Welcome to Module 4 of the workshop online tool for designing ventilation systems to reduce manure pit entry risk. In this session, we'll focus on mechanically cross-ventilated barns, and what we're talking about here are fan-ventilated barns with fans typically in the side walls and inlets in one or both of the side walls of the barn. What we will do today is first define the cross-ventilated barn design case. Then we'll create the input database for that mechanically cross-ventilated barn above a slotted covered manure pit. We'll review the input file, solve the example study. We'll do the simulation. We'll view the selected results, and then we will provide some interpretation of those results. So to review the situation we are talking about, this is a cross-ventilated barn above a slotted covered manure pit, full-size manure pit under the barn. You notice we have a fully slotted floor. The pit fan is located in the floor at the location shown at the center line. It can be located anywhere, but in this example that we're going to do today, it's located at the center line of the barn and close to the sidewall across from the barn ventilation fans. The three black circles are the barn fans. The barn airflow is basically a cross flow. I understand that there are some recirculatory patterns inside that barn, but the primary airflow direction is from the backside wall towards the ventilation fans. The air enters through air slot inlets at the eaves or at drop inlets, which we'll look at later on. The constraints and assumptions for this CFD simulation: the barn is ventilated with a negative pressure system, always. The pit is always ventilated with a positive pressure ventilation system, as we stated in previous modules, because the positive pressure system is a little less prone to short-circuiting in the kinds of situations we have in our slotted covered manure pits. The default conditions inside the manure pit are, again, that the manure pit is empty. We could have some residual manure in it, maybe 6 inches, maybe 12 inches, but it is not intended for a manure pit that is, say, half full, a quarter full, or 3/4 full. We're assuming there's no agitation of the manure during an entry event. We'd never recommend you go into a pit at that time anyway. So we're assuming no agitation and therefore little to no gas generation during the manure pit entry activity. The initial gas concentrations, the default conditions are 100 parts per million of hydrogen sulfide, 700 parts per million carbon dioxide, 15,000 parts per million of methane, and 240 parts per million of ammonia. Any of these noxious gas levels initial conditions can be changed. If you have a monitor or a gas detector and it tells you that your CO2 level is only 500 parts per million, you can certainly override the defaults. Oxygen initial content in the pit is 0 parts per million, and that is not changeable. So if you happen to have some residual oxygen in that manure pit at the beginning, the simulation program will give you some conservative ventilation times required to replenish oxygen, say, to 19.5% by volume. The manure pit default conditions, we assume that the manure pit draws its air from a mix of fresh and contaminated gas directly from on top of the pit. The user can change this by selecting a ducted fresh air option, and that is that you have fresh atmospheric air ducted into the building to the fan that puts fresh air directly into the manure pit. The default conditions are that there are no obstructions in the pit, there's no divider walls in the pit, there's no pump out annexes in the pit, that the pit is totally slotted, and that the pit fan delivers air in a direction perpendicular to the pit cover. Any one of these defaults here can be added or can be changed by the user during the data input process. The case study that we're going to simulate today is the same barn that we used for the tunnel ventilated example of module number 3. It's a fully slotted, 40-foot wide by 100-foot long by 10-foot high cross-ventilated swine finishing barn for 450 finishing pigs. The only difference between this one and the module 3 tunnel ventilated one is the type of barn ventilation. The barn is ventilated at the maximum ventilation rate, which is the hot weather rate for a fully stocked barn with 450 finishing pigs, which is approximately 55,000 CFM. The barn fan size and location, we have 3 52-inch diameter fans spaced 30 feet on center along the front sidewall. And the first fan is offset 20 feet from the left end wall. And it is located 3 feet above the pit cover. The barn ventilation inlets are continuous 8-inch wide ceiling slot inlets along both sidewalls. No blocking. The manure pit extends entirely under the barn, so it's 40 feet wide, 100 feet long, 8 feet deep. The manure pit ventilation rate's 9,500 CFM. The pit fan is located in the pit floor at mid-length and offset 4 feet from the sidewall opposite the barn ventilation fans. And that pit fan directs air vertically downward, perpendicular to the manure pit cover. The initial gas concentrations in the pit are 120, 70,000, 85,000, and 300 parts per million. Notice that the 2 in blue, CH4 and CO2, those concentrations are just reversed from the tunnel ventilated example. Just did that to make it different. So here's just a schematic of our situation. In the top, we have a top view looking down on top of the slotted covered floor. You see the yellow pit fan location and the general direction of the barn airflow. If you look down at the vertical profile down there in the bottom center, our barn airflow is generally from left to right to left, and our pit airflow is generally from right to left. The yellow arrow indicates the direction of the pit fan ventilation air entering the pit. To input the data, we access the website ventdesign.agsafety.psu.edu. Log in. Once again, you put in your user email address and your password. Log in. We come over here to create a new study. We'll click on that. And then you have to give yourself a new project name. Oh, now wait a minute. Up here, notice there's an underlined portion that says click here to copy an old study. Well, we're going to take advantage of that in this example because, our barn geometry and our pit geometry are almost identical to what we had already inputted for the tunnel ventilated project. Being basically a little bit lazy, I'd just as soon not have to input all that stuff again. So I'm going to take advantage of that. So I'm going to click onto an old study. And as soon as I do that, then that refers me back to the previous studies that I have inputted. I had a standalone pit, And that's not the one I want. And my tunnel ventilated barn above a full-size manure pit. Well, I'm going to click on that, and then I'm going to copy it and edit it. And what that will do is it will give me all the information that I put in previously for case study in module number 3. Now I got to change the title of this. I got to give it a new file name. So I'm going to change that to my cross-ventilated barn above a full-sized manure pit. And we're going to come down. Remember, you can fill in all these optional details. That's up to you if you want to fill that out. But we come to the bottom of the page 2 of this input data, and we got to change from a tunnel ventilated now up to a cross-ventilated barn. So I click onto that, click to continue, and we go to our pit geometry, and by golly, there we have it. My pit geometry, everything is the same, with one exception. Got to be careful. You notice our carbon dioxide and our methane concentrations changed, so I updated those to 85 and 70,000 parts per million as shown. Then we'll scroll down, and now in my pit geometry, my fan is still a 2-foot diameter fan, but my location of my fan is changed to an X of 50 feet. That's at the midplane. 50 is half of 100. And it's located 4 feet from the back wall, if you remember, so it's a Y distance of 36 feet. My X and Y offsets angles are still 90 degrees. And as we defined it in module number 3, the tunnel ventilation one. And now notice, I come over here now to barn geometry. Even though this is an old file, since I click cross-ventilated, the program knows that I need to input new information, possibly. Not all of it, because my eave height is correct, my barn length is correct, my barn width is correct, no problem there. But now when I go to my ventilation details, they are different. So it's asking for my fans. Notice I can select my fans to be in the front side wall, the back side wall, the end or in either end wall. Both my ventilation fans are in the front side wall, so I would click that. When I do, it asks me, well, how much ventilation, what's the total ventilation capacity of all fans in that front side wall? Well, it's 55,000 parts per million, CFM, so I have to input that. Then I have to click onto my fans. I'll go to my first fan. I got to locate it. So we're going to look at number 1. What's its diameter? It's 52 inches. How far is it? Where is it located? Well, it's offset 20 feet from the left-hand end. That's where the first one is located. It's at the vertical height above the ground is 3 feet, so my vertical offset is 3 feet. So now I've identified the first fan. Okay, I have multiple fans, so I'll click that. How many fans? I have 3. What's the spacing between the fans? Well, we define that as being 30 feet. If I had fans in other fans, I would, in other side walls or end walls, I would just click onto the appropriate side wall or end wall and go through the same procedure. But now we have to define our inlets, and we have inlets on the front side wall. They were 8 inches wide, so we input that. We said we have no blocking. If I had blocking, if I was going to block off portions of that eave, then I would click one of the boxes immediately below my slot inlet width input. But I didn't have any block offs, so I can be finished with that. But now I have inlets on the rear side wall as well, so I click that. Once I do that, I have to input my width. I have no block offs there either, so I finish that. So I have my inlets all in there. Now I've taken care of ventilation system for the barn. Now I have to locate my manure pit beneath the barn with my offset distances. And since it's a full-size pit, my X offset is 0 and my Y offset is 0. So I've got that taken care of. I just defined those two offsets right there. If I had a partial manure pit underneath this floor, of course, then my offset would be different. So now, if you recall, in the previous two sections, we said we can check our inputs by checking constraints. You click on that box, check constraints, and it'll work, and it'll do some computations of your inputs and check out some things. And if it comes back with no errors, that means that everything looks like it's probably okay. If there's some errors, as in module number 2, we had some errors, it would come back, give you an error message, and say you got to change something here. You're also given the opportunity to generate a preview as before. Click on that. It'll work while it's retrieving and developing and generating a 3D sketch. When it's done with that, it tells you that a preview is being prepared. And then when it's done, it says you can view the pit and barn preview. Click that. Then it says a 3D preview PDF. You click on that. And then you send the link. And it'll give you a PDF file, a rotatable 3D picture of the system. And this shows the fans in the right location of the barn, shows the right location of the pit fan. So, we start to get a little different comfort level about whether I inputted things correctly. And then, of course, you can go here, and this is just some of what it does with the menu. You can expand the figure. You can rotate it. And there's other things that you can do if you're interested in seeing all those features and things you can do to that 3D sketch. Either now you can pause this workshop and do it, or you can wait until the workshop is finished and then review the results files. Simply go to the website, click on the supplemental results files, select module number 4, then select under that the rotating 3D cross-ventilated previews, and you can do all the things that I just showed you on the previous slide, plus many, many, many more things. And you can get a pretty good idea whether you have everything inputted correctly for your barn and your pit. So now you're ready to save a new study. Again, I said before, we're paranoid about this, because once you save a study, there's no going back right now until it runs. And if you have an error in your stuff, or if you need to edit something, it's going to give you a run. It's going to be garbage, but it'll give you a run. And then you'll have to run it again after you correct it. So ask the question, is everything ready to be simulated? If you're really satisfied, then click OK. The study data will be sent to the computer, and it will tell you that you're going to be notified when your results are ready. It might be 30 minutes, it might be a couple hours, might be a day before you get an email back when the simulation is finished, but you'll get an email back saying, hey, your results are ready. And once that's the case, you access the website, ventdesign.agsafety.psu.edu. Click on View the Results. You have all these to choose from. And, of course, we want to look at the cross-ventilated barn. Click on the results, and you get the menu just like we got for tunnel ventilated. You have a whole bunch of animations of hydrogen sulfide, carbon dioxide, CO2, methane, ammonia, decay, and oxygen replenishment for different sections, different cross sections, horizontal and vertical. And then you have the results files down here. And that's where you access the decay curves. Same kinds of decay curves we had before. Hydrogen sulfide inside the manure storage. Remember, this isn't a single point. This is the maximum concentration of hydrogen sulfide anywhere in the pit. It gives the TPEL the time of ventilation to get to 10 parts per million and the time required to get to 1 part per million. Sometimes, to get down to that 1 part per million, we start reaching that point asymptotically, and we may time out. For example, in this case, we had not reached 1 part per million yet after 549 seconds of ventilation. But you look at this curve and you can see that we are so close to it that 549 seconds we might be at 2, 2.1, 2.5 parts per million. And I would argue that that's probably satisfactory, especially if we continue to ventilate during the entry event anyway. And then we get the same plot of hydrogen sulfide decay in the barn. This is anywhere in the barn, not a single point. It tells us that for at least some duration of time, up to 3 minutes, some portions of the barn have a concentration of hydrogen sulfide greater than 20 parts per million, which is the new short-term exposure limit for hydrogen sulfide as defined by OSHA. Of course, you can select more or less stringent short-term requirements, but what this says is that probably some parts of that barn need to be evacuated. Maybe not all of it, but some parts of it. We have to look at the cut plot animations to determine which portions need to be evacuated prior to a manure pit ventilation event for the initial conditions of this example. This is an oxygen replenishment inside the pit. That takes 327 seconds for the entire pit to have oxygen levels greater than 19.5% by volume. This tells us that there's portions of the barn that are less than 19% for almost 5 minutes. Now, not the whole part of the barn, but parts of it. And we have to look at the animation plots to determine which portions. And then we get the same kind of results for ammonia inside the manure pit, ammonia inside the barn, and we exceed 35 parts per million for some duration of time. So the same story. Got to find out, look at the animation plots to find out which portions exceed those short-term limits. This says how long it takes to evacuate the manure pit for carbon dioxide. 351 seconds before we reach the TPEL, the exposure limit. And inside the barn, it tells us that there's portions, again, that exceed 20,000 parts per million for almost 2.5 minutes. The animation plots would tell you which portions of the barn. And we'll look at those animation plots in just a few minutes. And then methane, same story, 523 seconds to get to the PL in the pit. And, for 2 minutes, the concentration inside that barn, somewhere in the barn, is greater than 25,000 parts per million for the initial methane concentrations of this example. So then you want to look at the animation plots. You click on the one that you're interested in, and this is an animation of the front midplane of hydrogen sulfide. You click onto that one if that's what you're interested in, or other ones. Look at them one at a time. We had looked at this in the modules 2 and 3. We'll look at it again. This is the barn and the manure pit. You see that sketched in the inside there. The big blue box up above represents the atmospheric air around the building. The part in red is the manure pit. The part in blue is the barn above it. This is a longitudinal of a vertical section. You see the 3 fans in that sketch. But more importantly, let's look at the legend. Blue is good. That means that the hydrogen sulfide content is 0. Red is bad. That means it's 100 parts per million or greater. And the pit, as we expect, is, this is probably early. This is only 10 seconds after the initiation of ventilation. The red portion in the pit, that's pretty high concentration yet. And inside the barn, we have a lot of blue area, but we also have some of that green and light blue areas, which are, at 30, 40, 50 parts per million. So that is not looking too good in all parts of the building. I want to point out that the other gases, the same color scheme for the contaminant gases, blue being good, red being bad, but the parts per million are quite different for the same color. So you have to, view these cut plots for different gases on these 4 relative scales, and be sure to pick out the right colors for problem areas and non-problem areas. In the far right, we have the legend for oxygen concentrations. The color scheme there is reversed because of just a nuance in the CFD package we used in the reporting process. For oxygen, blue is bad, that's 0%. Green is good, that's 19.5 to 20.5% oxygen. So just be aware of that, and it's not a problem. So now we'll scroll down. In the online tool, we have sketches there that help you define the vertical and the horizontal cut plot planes. And then here are some examples of 4 cut plots for hydrogen sulfide for the cross-ventilated barn. This shows, wow, we have a lot of areas of concern inside that barn, and they're scattered pretty much throughout a large portion of that barn. Let's go back and let's view that again. You see we have some pretty large portions that are red, light green, and certainly pale blue, and those would be problems of concern. But after 280 seconds, the whole domain is all blue and all okay. So we had to evacuate pretty much for the conditions of this design example, this case study, we'd probably have to evacuate all of that building before we would dare ventilate it. And then this shows the front midplane. This is a vertical cross-section in the front quarter section. And you notice in that we had a pretty large section that was contaminated. This is the midplane of the manure pit. And it shows after about 270 seconds that is evacuated. And this is the right midplane. Now all the optional features that we described in modules 2 can be added to this example. Rectangular cover openings, divider walls, pump out annexes. We can locate the pit fan in the annexes. We can add obstructions. We can change the direction of the airflow into the pit from the pit ventilation fan. And some of the other things, we can add additional fans to the barn. In the barn, the barn ventilation system. We can have fans in both side walls, fans in the end walls. We can have inlet slots in the end walls. We can block off portions of those inlet slots anywhere. We can use inlet windows instead of inlet slots. Some ventilation systems use adjustable windows in the side walls or end walls for their air inlets. You can certainly do that in place of eave inlets. If you have a very wide building, you can use drop inlets as well. And you can have baffles and block-offs and so forth in those drop inlets, in the interior ceiling portion of the barn. At the conclusion of this presentation, if you would like to view more leisurely and more completely the results, the decay curves, the replenishment curves, or the animations for any of the gases, you can do that by going to the website again, clicking on Supplemental Results Files, and selecting Module 4, and then under Module 4, select those results files that you would like to review more completely and in a more leisurely fashion. And with that, we will conclude this presentation, workshop presentation on the cross-ventilated barn above a slotted covered manure storage. The next session will be a student participation project where you will have the opportunity to input data for a given case, and you will be able then to generate your set of results and compare them to results that we provide for that case. If you have any questions or comments, you can contact me at hmanbeck@engineering.psu.edu or Dennis Murphy at djm13@engineering.psu.edu. Thank you and have a good day.